Hey everyone, and welcome back. So what made this challenge so much fun is that it was a normal printf sort of exploit, but instead of the buffer living on the stack, it lived in the data section. And this makes things slightly more challenging because normally when we do a printf sort of exploit, we actually send the server two different things. One is the %n modifier, so we get our arbitrary write. We also usually send address pointers so that they're located somewhere on the stack so that we can reference them. But since the buffer in this challenge wasn't on the stack, we can't reference an arbitrary pointer to do our arbitrary write. So that means we have to find existing stack pointer gadgets already on the stack, and it just adds another layer of complexity, which is fun. So this was printfail as part of UTCTF. It says I managed to break Pwn Tools with this. It was written by JB Yoshi. We're given a netcat port and a download file. So if we look at what this challenge looks like, it says I'll let you make one printf call. You control the format string, no do-overs. And we can tell it's a printf format bug since we can do some %ps, so %pointers, and we get some values off the stack. And cool. And so already here we can see this looks like a main text section leak. Cool. Let's take a look at checksec. Oops, checksec. It says full rel canary, everything's enabled. So that means we're going to have to call printf multiple times. We need some info leaks, and yeah, there's just no way to exploit this in a single run. So let's take a look at Ghidra. So now that Ghidra's loaded, we can take a look at the binary. There's two functions. There's the main function and the run round function. The run round function is where our printf vulnerability is. We can see it's doing this printf on a buffer. If we kind of follow that back, it's going to be doing an fgets on this buffer for 512 bytes, and previously it did a memset. Cool. It's also going to do this thing where it calculates the string length of the buffer that we inputted, and then it's going to check to see if it's less than 2. And that's useful because there's this check here that says if that variable is not equal to 0, it'll print, hey, that was an empty string, come on, you gotta at least try, okay, I'll give you another chance. And so the challenge author basically gave us a way to repeatedly call this printf. We just have to trick the program into thinking that that input buffer was 0, and we're going to do that by using the printf exploit. Since that variable is defined on the stack, we can just use that printf exploit, figure out what offset that is. I think in this case it was actually 7, so if we do a $7$n, we can set whatever value we want there, like 5, and that way we'll be able to repeatedly call printf. So that's step 1, so we can call printf multiple times. We also need the info leaks, which is easy because it's a printf exploit. You just do a bunch of %ps and we're going to leak a bunch of values off the stack. And we need an info leak for the main text segment. We need an info leak for libc because eventually we're going to do a one gadget, and we need an info leak for the stack. It would be nice if we didn't need one for the stack because the stack can be a little bit finicky, but if we look, we see full rel is enabled. So normally it would be nice to overwrite a global offset table entry and just jump into a one gadget or a system or something like that. Unfortunately, that's not possible. Actually, this would be a perfect case for overwriting the global offset table entry for printf with system, because then on the next call, you would just enter, when it's going to do that printf call with your input, you could just do system bin shell, but we can't do that, so we have to do a one gadget. And since the rel is here, we're going to overwrite the return address that's on the stack. Cool. So another important part for making this whole exploit work is since the printf is very stack dependent, we really want to match our local environment to the remote system. So I don't know, if you were playing the CTF, you probably saw that I asked for what version of Ubuntu, if they're running Ubuntu. Very important that you do that, otherwise things just don't line up and writing these exploits gets super frustrating super fast. So for this exploit, they were using 2004, Ubuntu 2004. But yeah, we have all the gadgets we need. We have a way to repeatedly call printf. We have a way to get our 3 info leaks. We're going to calculate the one gadget, and we're going to figure out where that variable lives on the stack. And then we're going to do a couple of printf trickeries to overwrite that variable on the stack such that it points to the one gadget, and then when we return from all of our functions, it should just pop a shell. All right, so the code is a little bit non-trivial because, like I said earlier, normally when we do a printf exploit, we're just going to use the scratchpad right here. Normally when we do a printf exploit, I think most people know that you're going to use this %n, and what's going to happen is it's going to take a variable that's on the stack, and it's going to treat that as a pointer and write to it the number of bytes that have been printed out so far. So if you were to do something like sjp and then %n, actually let's do this, whatever variable is on the stack that's being accessed right here, it'll write the number 3. That's cool. The problem is, And so normally when we do a printf exploit, what we'll actually do is we'll actually put in, some hex address like right here. I don't know, pretend this is, some valid address, and then we'll do a %end, and we'll actually figure out what offset this is. So pretend this variable, when we write it onto the stack, the buffer is on the stack, and we'll say %for for $n is this offset. And this is a very powerful primitive because now we get to do an arbitrary write because we're also supplying the address. But in our case, what makes this challenge difficult is since the variable is, the buffer is defined in the data section, it's not on the stack. So we can't just insert arbitrary addresses. We have to reuse existing gadgets that are already on the stack. So hopefully that was clear. But we can take a look and see what that actually looks like. So this is the solve script. This is about as long as it is, so we can see there's a little bit to it. I'm going to go just a quick run through, and then we'll go through a little bit of details. So high level view, and then we'll kind of tunnel in. So like I said, step 1, we want to find a way so that we can repeatedly call printf. And I do that with this this call right here. I found that the empty buffer stack variable was the 7%, and I'll show how I do that in a second. But as long as I include this, it's going to overwrite the pointer to the 7th element on the stack with how long this is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes. So that have you written any bytes is now going to be the number 10, which is not equal to 0, so we get to repeatedly make calls. This is how I do my info leaks. I'll show how I calculate these in a second. But I'm basically saying print out the 17th pointer on the stack, then the 43rd pointer on the stack, the 13th pointer on the stack, and the 7th pointer on the stack. And from there we have all of our info leaks. Cool. So what made this challenge fun is we had to find an existing pointer on the stack. I found that the 15th pointer on the stack is a pointer to another variable on the stack. Again, I'm going to go through GDB. I'm just giving a high-level overview. And so using that, I can then write to that address on the stack. The address that it was pointing to on the stack is the 43rd pointer on the stack. So now I can write to that one. And so I take that first pointer that points to the stack, I'm going to write to it the value of the return address also on the stack. And then I'm going to write, because the way when you do that %end, it's writing the number of characters that are on the stack. If you do write 3 bytes at a time, that can be many millions of bytes, and I just don't want to send megabytes of data back and forth. I actually do 2 separate calls. So first I'm going to write the first 2 bytes of the one gadget, and then I'm going to write the last byte of the one gadget on top of the return address. Anyways, so we write the third address. So I said I move it up 2 bytes so I can write the third address, the third byte of the address, and then I write the third byte, and then from there we should just have shell. So if you're just looking for a recap of what the exploit looked like, that was it. Now I'm going to go into like the stack and GDB, and I'm going to kind of like show where the address is and how to calculate the offsets and get into some of the more kind of hands-on sort of technical stuff. All right, so the first step was finding the offset that'll allow us to repeatedly make those printf calls. I'm very lazy. This is what I did during the CTF. I just put it in a for loop and I see which one doesn't exit. So this is a script called fuzzsolve. It's going to start the process. It's going to receive until no do-overs, and then I'm going to send the line Sloppy Joe Pirates for life, and then I'm going to send the I $n %p. And so this is going to continually jump over, and normally the program will exit, and so then it'll just jump over again. But at some point it'll hang because it's waiting for more input, and I know I have the correct offset. So if we run this real quick, Python 3 fuzzsolve, we can see it sent $1, 2, 3, 4, $5, $6, $7. So this was the 7th offset, and at this point we get the response, hey, that was an empty string, come on, you got to at least try. You could go through the GDB and like figure out what value it is, but it's very easy to write this little fuzzer real quick, and so that way we know it's the 7th offset. So the next step is calculating our info leaks. So to do that, we're going to use GDB. So we do pwn GDB attach to the process. We're pretending I don't know what these values are. Let me save these for later. We're going to then do plus %p space times 50. So we're going to print out 50 pointers on the stack, and we'll do a p.interactive. And that way it hangs. So let's Python 3 solve. We'll continue, and here are our info leaks. A whole bunch of them. It's a beautiful thing. So let's run a VM map. This will show us all the different sections within the binary or within the process. So here is the stack. So we can see it has addresses that start with 7FFC, and we can see here's a 7FFC, 7FFC. So we have 2 stack leaks. To calculate the base from our leak, it's pretty simple. Basically, we're just going to, the stack is going to be at a different address every time we run this, but we just need to calculate the relative offset between our leak and the base of the stack, because these things will always be at a known offset, just they might be floating around, but they're always going to be a relative offset from the base of the stack. And technically we want the top of the stack, because if you remember, the stack goes down, so I shouldn't say the base of the stack, we technically mean the top of the stack. So there's our stack leak. Then we also need a libc leak. If we look for libc, here's libc. It's going to start with a 7fc0. So we start looking for a 7fc0, and here's one. So we have a libc leak, and we're going to calculate to the base of it. Then we also, I don't actually think we need a main text segment leak, but I always just include it because it's super simple, and so we can see we had one right here. Just for funsies, we can see, where are we? This is, so we printed out Sloppy Joe Pirates. So we also, if you remember, we used the 7th offset to store our is empty string buffer repeat variable. So if we count 1, 2, 3, 4, 5, 6, 7, this should contain 10. And it contains 9. Did I count wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, my bad, 9. So we can see we overwrote the value 9 because we wrote these 9 bytes. Then we did that %7n right here. And so we wrote the variable, or the value 9 to that variable, and that's why we get to repeatedly call. But anyways, that's how we do the info leak. So if we look back at the self script, you basically just copy these out. So let's say we want to do the base one. I forget which one I used, but you would just copy like this one. Let's say we're using this. I'm going to put it here. And then we subtract where the real elf base is. So this is the real elf base. And if we look at this, let's take this. We'll print it out here. So we know that when we leak this value, it is always 16,000 bytes away from the base of the main text segment. Again, the address will float, but it'll always be this far away from the base. So whatever variable we leak, or whatever value we leak, we just subtract this amount, and we'll be at the base. And so you can see that's what I do for these. Here's the elf base, the top of the stack, and the libc base. I just subtract them. Again, the stack is a little bit weird because the stack goes down, so you actually want the top stack address. But here's the stack leak. And that's pretty much how I do it. To actually, yeah, that was it. Cool. Now comes the slightly more difficult part. We have to do some weird stack stuff. So let's fix this. Back to what it was. So we have our info leaks. We no longer want an interactive there, and we'll put GDB somewhere else. Cool. So somehow I calculated the stack return address, and we're going to write our first address here. So we're going to go to here. Let's actually break on printf, and I think that should be good. Continue. So now we're at printf. Like I said, we need a way to, we don't have arbitrary pointers, so we need to create our own pointer so that when we do the %n, we can write to a variable we want. And so we're going to do that by finding a variable on the stack that points to another variable on the stack. And I think the one I was using is this one. So at this stack address, it contains this stack value, this 8318. And if we see, it is actually down here, right here. So this 8318 is pointing to another stack variable, and it's pointing all the way down there. What we're going to do is we're going to do the %n. We're going to reference this stack pointer, and so when we do %n, it's actually going to overwrite the variable here. So we're going to take this. We're going to overwrite this variable because it's currently pointing to this address with another stack variable that points to the return address. And there's a return address here. Actually, we're going to be using this one. You can see it's a libc address. Cool. So to repeat, we're going to take this stack address. We're going to calculate what its offset is. We're going to write a value here because this is where it's currently pointing. So when we do the %n, it's going to overwrite this variable. And we're going to overwrite this value instead of printing or pointing to whatever, the string somewhere on the stack. We're going to have it point here. And so that's our first one. We needed to calculate this variable, very similar to how we do the info leaks. Let's see, do I calculate the stack return address? I figure out where, oh yeah, I did this a little bit weird. I found another local leak. I just took one of those leaks, I guess this one, that was part of from previously. And I just found this one was very close to this return address, so I just used it. Basically, you're gonna leak a value. It's gonna be like something like this, and then if it was this leaked value, you can just see it's 8 off. So you just subtract 8, or sorry, you add 10 hex. So that's how you calculate that info leak. So we know what this address is, and do I print it out? I hope that I print it out. Yep, I print it out here. So I say this is the stack return address. So this is the variable that's going to be popped off the stack and executed from, and that's our target. That's where we want to write our one gadget to. Okay. So if we look down here, hopefully you can see this. So we're doing that %7$n, and so that's going to overwrite that variable so we can keep making printf calls. I'm going to then write out 27,382 characters, and that'll set a value equal to this, the last 2 bytes. So this and this should be equal, and I'm going to write it to, oh, sorry, actually, my bad, we're right here, I'm sorry. We're going to write out 33,000, that looks a little bit closer, and we're going to write it to the 15th variable. And this hn means only write 2 bytes. So we're going to overwrite this stack pointer here, so that this points to this, and we're going to overwrite the last 4 bytes of this. And so now this should point there. And so if we continue to the next printf, should do that. Anything else nope. Cool, we should be at printf. Let's do another stack 20. Actually stack, what do we do, 40? So we overwrote this one with this. So now this address, 28, somewhere down here. Oh, 318, sorry, this address. So now instead of pointing to that, that chow binary name, it's now pointing to this libc, this 228. So hopefully that made sense. There's these things get tricky. I think it's best just to kind of sit down and do it yourself. But so now we have a variable that is pointing to this address. So now we can use this as our %n, which we can't see. It's going to be up there. But let me just go back here. Now we can use that as our %n, where we will here we're going to write the 43rd index with this one, and we're going to put in the lower 2 bytes of the one gadget. And you can see I'm doing the one gadget address. I'm taking the lower 2 bytes. I'm subtracting 11 because I already write 11 bytes out here. And that'll start writing the one gadget to our return address that's going to be popped. And so right now it's pointing to libc main, but if we continue again, we do a stack 40, we should see it's pointing to something weird, init cache info. That's because we still need to write, I only wrote the last 2 bytes, and now we need to write this byte. And like I said, I'm doing that because you can see how I'm outputting a bunch of garbage up here, because we need to write that many characters before we do the %n. Just this way, if you split it into 2 separate writes, it doesn't write as much garbage. Cool, so at that point we're going to do the whole process again. We're going to move this pointer down here. So instead of pointing at this address, we're just going to bump it up 2. So instead of pointing at 28, it's going to point at 2A, or yeah, 2A. Move it up 2 bytes, and then we're going to write 1 more byte. And we do that again. We'll do another stack 40. Do I need to continue? Stack 40. Am I in printf? I think I joined the dash program. I joined shell, but you'll just have to believe me that. We can go back and check it, but basically we wrote the full one gadget, and yeah, shell, you probably saw bin dash started, so that means we got shell. I'll rerun it for real, and we can see what shell actually looks like. To get the one gadget, since we're in the same Ubuntu box that is being run on remote, we already have libc loaded. It's the same libc. So you can do libc, it was called printfail, I think. You can see where libc is being loaded from, so it's being loaded here. So I just take this, I copy it, I already have it, but we'll just call it libc.so.6, and then from here we can do a one gadget, libc.so.6, and we can get some addresses. I forget which one I used. Let's see, where do I calculate the one gadget? Where do I calculate it? One gadget? Here. So I ended up using E3B01. So I guess I used this one, E3BO1. I probably saw that the registers just looked good at that point. Yeah, and pretty much that was it. We write the one gadget, and the one gadget will jump and start calling shell. So we can, I think remote is still live. So thankfully, again, since we're on the same type of box, everything should just work. I switched it over to the live port. We'll do a, oh, and we also need to get rid of GDB, because GDB does not work remotely like that. And we pray. Didn't see anything exit, and there we go. We have shell. So we can cat out the flag, cat flag.text, uflag, one printf to rule them all. So again, super fun challenge. It's a very fun twist when the buffer exists on the data segment instead of the stack. We have to do that extra like pointer math through the stack. But overall, very fun challenge. Definitely made me question myself, and which is always good. And yeah, let's see you at the next CTF. Cheers.